everyone. We are the Pocket Oscilloscope team. I am Alec Peng.
I'm David Nguyen.
I'm Jihee Yu.
And I'm Han Liu.
And this is our project.
Our 362 project, we create a pocket oscilloscope, and this is our product. So in front you see we have two rotary encoders which serves to scale in X and Y direction. So when you press the button, it's gonna enable the scaling mode, and press it again, it's gonna deactivate that. And then we have two buttons. One does the waveform capture to stop the waveform from moving, and then one button is to serve as a function generator. And we have two batteries in front, and on the back we have 5 batteries to power up the oscilloscope.
Okay, so there are a few functionalities on this board. The first one we have is it's going to take an input from the DAC pins here, and it's going to display a graph. Currently we're running a sign test wave to show you what the other buttons are doing specifically, but basically we'll take an input right here on the DAC pin. And then for these buttons, we have the first one is shift Y, so you can shift up and shift down by turning right to shift up and left to shift down. The second one is you can scale the scale Y axis, so you can turn right to scale it up or turn left to scale it down. And the maximum scaling for Y direction is 10 volt per div, and minimum is 1 volt per div. And for the period, you can scale this X here. It's going to display it when you click on the button, and then you turn right to increase the amount of second per div, and decrease by turning left. And you can pause the waveform right here. So if you click on this, it's going to show, it's going to pause the waveform up, basically. Yeah. Moving on, we'll have the DAC, which Jihee will present.
For my part of the project, I implemented the DAC functionality for our oscilloscope. In our project, we needed a DAC because we wanted the oscilloscope to be able to generate the signals as well as measure them. I generated different waveform sine, square, triangle, and sawtooth using a wavetable. A phase accumulator steps through this table at a rate that depends on the selected frequency. Each value in the table is converted into a PWM duty cycle, and after filtering the PWM, the signal behaves like an analog voltage. This allows our device to output test the signal directly from a GPIO pin. The user can loop this output back into the ADC input to verify that the oscilloscope is capturing signals correctly. Overall, my DAC module provides an integrated waveform generator that makes the oscilloscope more useful and self-contained.
Okay, so the reason why we actually made something like this is because there's a lot of instances where maybe you're trying to debug something where that's very difficult to move, and so instead of taking your product to the oscilloscope, it would be a whole lot easier if you could take the oscilloscope to the product. For instance, one of the team members here is actually in Purdue solo racing, and a lot of times it's maybe not even feasible to take the car to the test bench. I say test bench, it's not really a test bench, but
Cut it.
bro. When I used to work in a manufacturing plant, actually there were a lot of times where I wished I had something that was portable so I could go measure the signal coming out of maybe some instrument or some measurement device, and I didn't really have that. So this is a possible solution to that fills that niche. You can take this and put in your pocket and go wherever you need and measure the signal. You can take this, put in your pocket, go to wherever it is that you need to measure, and measure what it is that you need to measure. You can also use it as a makeshift voltmeter. This thing can measure this thing can measure plus or minus 12 volts. So you can measure up to a full car battery with this thing. And lots of signals in the plant that may be around 12 volts or so.